Welcome to the Explainer. If you've ever actually stood on an offshore platform surrounded by nothing but open ocean, you completely understand that power is literally the lifeblood of the entire operation. Without it, everything just stops. So today, we're taking a deep dive into synchronous machines. We're going to explore the core engineering principles that keep these massive, isolated power systems running, stable, and above all, safe. Let's jump right into the heart of the platform, right where every single watt of electricity begins. It's honestly kind of wild to think about. This massive, heavy-duty operation entirely relies on the tiny air gap between a spinning rotor and a stationary stator. It's right there, in that invisible magnetic space, that raw mechanical energy from a gas or steam turbine is transformed into the exact electrical power that drives everything, from your heavy refrigeration compressors all the way to those life-saving navigation lights. So here is our roadmap for today. First, we'll cover core principles. Next, generator reactances. Then, selecting voltage levels, maintaining stability, and finally, commissioning tests. All right, Section 1, Core Principles. Let's look at the fundamental physics. This equation right here physically represents exactly how mechanical rotation inside the rotor translates into electrical frequency on your grid. It's straightforward. Frequency, or F, equals the number of poles, P, multiplied by the speed in RPM, N, and then you divide all of that by 120. So if you've got a 4-pole machine spinning at exactly 1500 RPM, the math works out perfectly to a stable 50 Hz grid frequency. It's this elegant, totally fixed relationship that entirely dictates the mechanical design of your prime mover. Moving right along to Section 2, generator reactances. We have 3 distinct states here. When a fault strikes, those first few milliseconds are literally violent. From 0 to 0.1 seconds, the subtransient reactance is at its absolute lowest, usually hanging around 0.1 to 0.2 per unit. Because this resistance is just so incredibly low, this state dictates your immediate, absolute highest peak fault current. If you're out there sizing circuit breakers to survive a massive explosion of short-circuit energy, this is really the only number that matters. Right after that initial explosion, the transient reactance takes over. This lasts from 0.1 up to about 3 seconds, and this reactance is slightly higher. This specific time frame is absolutely critical for system stability. It's what actually gives your protection relays those crucial milliseconds they need to detect the fault and coordinate trips, well before the generator falls completely out of synchronism. And then, finally, things settle down. We reach a steady state with the highest reactance value. Occurring after 3 seconds, the synchronous reactance represents the machine's sustained short-circuit current. Basically, it's the baseline impedance that governs your day-to-day, steady-state voltage drop and the overall load flow conditions across the entire platform. Okay, Section 3, selecting proper voltage levels. This is a huge one for us. Due to the extreme physical constraints of an offshore platform, choosing the right voltage is arguably the most important decision you're going to make. Think about it. Onshore, you might have acres of open space for massive substations, but offshore, every single square meter is prime real estate, and your equipment size is severely limited. So this rule of thumb table is vital for navigating those constraints. Notice how your system rating completely dictates your voltage range. If you're generating somewhere between 500 and 1000 kVA, you're generally sitting between 400 volts and 7.5 kilovolts. But watch what happens as that power demand grows. Between 1000 and 10,000 kVA, the floor shifts up to 5 kilovolts. And once you jump above that massive 10,000 kVA mark, you are exclusively looking at the 6.6 to 15 kilovolt range. You can really see here how, as the kVA rating increases, that practical voltage range absolutely must shift upward. Why? Well, because massive currents generate massive heat. By stepping up the voltage, you drop the current. That allows you to shrink your incredibly heavy cables in your switchgear down to a size that actually fits inside a cramped offshore electrical module without melting everything down. If you take one number away from this today, memorize this one, 6.6 kilovolts. This is the industry standard and by far the most common offshore voltage for loads above 1 MVA. While extra high voltages are definitely used for those long subsea transmission runs, on the platform itself, 6.6 kilovolts is the absolute sweet spot. It perfectly balances the need to reduce current for space saving against the thick insulation requirements of your switchgear and motor control centers. Now, when distributing all that power, you've got to differentiate between low-voltage vital loads that keep your personnel alive and high-voltage essential loads required to black start heavy machinery. Vital loads, so think communications, emergency lighting, and navigation, operate at 380 to 415 volts and are basically always backed by UPS battery systems. Essential loads, on the other hand, well, those are your massive 6.6 kilovolt induction motors required for restarting complex LNG refrigeration processes or running your main firewater pumps. All right, on to Section 4, maintaining system stability under heavy loads. Your generator is perfectly happy and stable right up until that load angle delta pushes past 90 degrees. At that exact point, you risk complete and total instability. As demand increases, the rotor essentially advances ahead of the stator's magnetic field. If a sudden, massive load spike pushes that angle past 90 degrees, the magnetic bond physically snaps, the generator slips a pole, and suddenly you're facing a catastrophic, total platform blackout. Which brings us to Section 5, essential commissioning tests out in the field. This is where all that theoretical math slams into the real-world responsibility of an engineer. Imagine a generator sitting on the deck of an offshore platform. It has just endured a brutal, salty sea voyage. It might have absorbed marine moisture or suffered heavy vibration damage on the way out. Because of that, you've got to follow a really strict chronological progression here. You start passively, measuring copper winding resistance, and then moving on to Megger and PI tests to hunt for any moisture. Only when that machine is proven completely 100% dry do you even dare spin it up for open and short circuit tests. And finally, you hit it with the ultimate trial, the high potential stress test. And you really need to know these past criteria by heart. Things like achieving greater than 100 megaohms on a new Megger test, or seeing absolutely zero breakdown during a high-pot test. That high-pot test, it is the ultimate stress test. You're applying twice the rated voltage, plus an extra 1,000 volts for 1 full minute. If the insulation holds strong without breaking down, congratulations, your machine is finally ready to sync to the grid. Okay, let's bring all of this theoretical and practical knowledge together for a quick recap. We have covered a tremendous amount of ground today, from the microscopic air gap all the way to the high-voltage switchgear. Just remember the key takeaways. Subtransient reactance is what drives your immediate fault calcs. A load angle creeping over 90 degrees will cause massive instability. 6.6 kilovolts is your standard offshore voltage for anything over 1 MVA. It's the absolute linchpin that allows those massive generators to deliver power without needing impossibly huge cables. And of course, always follow that strict pre-commissioning sequence. So, the next time you're stepping out onto a rig, try to bridge that gap between academic theory and practical engineering. When you look at one of those massive emergency systems, ask yourself, are the invisible physics, the precise reactant states, and all that rigorous testing really enough to guarantee that power will be there when the crew's lives actually depend on it? Thanks so much for joining me for this explainer. I really look forward to seeing you in our next session where we're going to tackle automatic voltage regulation, which is the critical component that actually controls the very excitation field we've been talking about today. Catch you then.